Hello everyone. This time I want to review the KSAT math problem for the admission year 2024. In this case, the calculus optional subject, the problem number 30, the problem type is odd. KSAT is for Korean Scholastic Aptitude test. We take this test once a year, so many student, high school student, they fully focus on taking this problem. Okay, anyhow, this problem is a calculus problem. We have a full uh, formula of its derivative. The original function f is differentiable on the all real numbers, and we have its derivative function. Here it's a periodic function because the function is sine times its cosine. Sine has an absolute value outside here. And then another function introduced here is a tangent line at a specific point, positive x coordinate, let's say A, and it looks like when you have a graph of function of f, there's a x coordinate, and then at the point of A here, we have the point A comma f of A here, this point. And then we can draw its tangent line. It looks like this. Okay, so right now the value of x is not constant. So the tangent line actually depends on the value of a. So by moving this value of a from, let's say, 0 plus to the infinity, we can get the tangent line of y equals f of x for the all positive x here. It's the context of this problem, and the main point is we have introduced a new function which is original function minus its tangent line function, and take integration from 0 to certain x. We define this as a new function of x, h of x, and here we are interested in at which point the function of hx has local minimum or local maximum. We want it has many solutions. It has many solutions because the original function is periodic, so this local maximum and local minimum should repeat. It has a certain rules in it. It could not be the same as the periodicity of the original function, but it should repeat each process, and it has infinitely many local maximum or local minimum once it has at least one local maximum or local minimum. It repeats. So we can, for the positive a, we can make a sequence. The rule is the smallest one and the second smallest one, and we make a sequence A1, A2, A3, A4, and so on. Here A6 here, and then we are required to find this value here. This is an introduction of this problem. So let's take a look at the point of this problem. The first one, can we resume the graph of y equals f of x roughly from its derivative? Once we can have the graph of the each original function, and then we can imagine its tangent line at each point, and then it will give us an advantage to guess the relationship between f of t minus g of t. This is actually the second point. What's the meaning of f of t minus g of t? And take its integration from 0 to x here. So the original function minus its tangent line what's the meaning of this one? A relationship with local maximum and local minimum. How it is related to each other. So those are the 2 points of this problem, and luckily, probably, they will give us some rule to figure out the local minimum or local maximum value of the function h of x, and then we can find the value here. Okay, let me give you the big picture. I'm not give you specific details or logics to solve this problem, but I want to give you some clue or the point how to approach this problem, what it means for us, what is related to how it is related to solving this problem. Okay, let's start. First, we have to use its derivative f prime of x since the absolute value of sine of x it's a periodic, I said, so let's consider the domain from 0 to pi and pi to from pi to 2 times of pi. In this region, sine of x is positive. In this third or fourth quadratic plane, the sine of x is negative. So the derivative is sine x times cosine x. The below one is negative sine x times cosine of x. And here we could figure it out that this is 1/2 times sine of 2x. This is negative 1/2 times sine of 2x because of the angle sum rule for the sine of x, because sine of 2x sum of angle, this gives us 2 times sine x times cosine of x here, because okay, anyhow, and then let's see the graph of f prime of x. The graph of f prime of x, let's consider it a positive domain here. It's about the function of sine of 2x. It has a periodic function, periodicity pi. So let's consider pi and 2 times pi, and there's a 1/2 of pi, 3/2 of pi here. 1/2 times sine of 2x has a maximum value when x is pi over 4. The graph looks like the maximum value is 1/2. So here, and then when x is 1/2, 2 times 1/2 is 2 times 1/2 of pi is sine of pi, which is 0. So it goes to this point. And then since it's periodic sine function, it reaches to negative 1/2 when x is 3 pi over 4, and then it goes back to pi. And in the domain between pi and 2 pi, there's only difference of negative sign, so we repeat each graph, but with the opposite sign. So from pi to 3 pi over half, it looks like this, because this part converted to like this here, like this, okay? And then this part from 3 pi over 2 and to pi, it will look like this one, because here from pi over 2 to pi, its opposite sign looks like this one. It corresponds to this one. Okay, here we have a full graph of each derivative function. Say y equals its derivative f prime of x, and it's a periodicity. Its periodicity is 2 times pi, because of the absolute value of sine of x. Next step, I'm gonna guess the graph of original function f of x right here from 0 to x, y equals to f of x. One concern that we have to do is from the derivative of this one, we cannot determine the constant term from its antiderivative. Constant term usually determined by specific point at certain point, let's say 0. F of 0, let's say here, it is 0 for the convenience, and then the constant term is determined. It is without generosity, so without generosity I can assume that f of x is 0. So it starts from the origin, and let's consider from 0 to 2 pi, because the periodicity of the antiderivative is 2 times pi. So the original graph f of x repeats. Okay. The first part, it has a positive derivative from 0 to pi over 4. Here, pi over 4. So, and then its derivative increases, so it's concave up here, concave up. From pi over 4 to pi over 4 to pi over 2, its derivative is still positive. That means original function increases, but the absolute value of f prime of x decreases, so it's a concave up. So the graph looks like this, concave up. Okay. Oh, I'm sorry. It's a concave down. And this part from 0 to pi over 2 is concave up, concave up, concave down here. Okay, I'm sorry for that. So it changes its shape of graph at the point of pi over 4. And if you see the periodicity, and it repeats the same patterns as it goes as the x value increases in the f prime of x, and we can easily guess the next shape of the function. It looks like this, concave down, and then from here 3 times pi over 4 to pi, the absolute value of f prime decreases, but it goes to 0, so it's a concave up here. And then here we have another negative derivative, so it goes to the negative value here. Here is 5 times pi over 4, and it looks like a concave down, and then another negative derivative will gives you decreasing function, but concave up here. Okay, and then last part will be positive derivative here. It is 7 times pi over 4, and its graph goes to concave up till 7 times pi over 4 and concave down to 2 times of pi here. So in summary, the shape of its original function y equals f of x is a periodic function with periodicity 2 times pi, but its characteristic is that it changes shapes of the function. Concave up, usually concave up, its second derivative is positive, and concave down, its second derivative is negative. So concave up, concave down here, and then concave up, and concave down, concave up here, and concave down, like that. And it repeats this process here, concave up, concave down. Okay. Okay, go to the second point. What's the meaning of function h of x? The tangent point a comma f of a is undetermined. A is not determined here, but the original function minus its tangent line and its integration is a function of h of x. Let's take a derivative with respect to x, and then we have f of x minus g of x here. To have a local maximum or minimum, let's say at point x equals a, it's a tangent point. To have a local maximum or minimum at the tangent point a comma f of a, then the sign of h prime of x, its sign changes its sign around x equals a. It's a local property. Around this point x equals a, we have to check whether the h prime of x changes its sign. So that means, for example, let's consider y equals x cubed for the original function here. Okay, and its graph looks like this. Its graph is equals to, it's a concave down and it changes to concave up, concave up, concave down. At the point of the origin here, and then its tangent line at the point A here, certain point A, looks like this. It's tangent line here. So in this case, at the local around this point of A here, around this point here, f of x is always bigger than its tangent line, g of x. In this case, around x equals a here, when a is positive. But when you consider the tangent line at the origin, obviously this is not for this case, because on our problem a is a positive value, but it's just an example here. Let's say a equals 0 and the tangent line is x-axis, because its derivative is 3 times x squared. Its derivative value at x equals 0. Its slope of this tangent line is 0. So it's a parallel line passing through the origin here. When a equals 0 here, around this point, the origin here, when x is negative, the original function f of x is less than the tangent line, is below. So it's negative for the negative x. And for the positive x, its original function is above the tangent line. So it is positive for the positive x. So in this case, we can say that h prime of x changes its sign at its sign around x equals 0. That means when a equals 0, h of x has, in this case, it has a local minimum, because the sign changes from negative to positive as x increases here. So what all this example mean to this problem here? Can we more generalize this situation to our original problem? We can think that in the functional graph, whether concave up or concave down, its tangent line at any point, its tangent line does not passes through its original graph y equals f of x. It does not passes through. So around the tangent point here, the sign of its original function minus its tangent line is here. In this case, f of x is always below the tangent line. So f of x minus f of g of x is always negative. For the concave up, in this case, sine of f of x minus g of x around this tangent point is always positive because the original graph is above the tangent line here. Okay, it never happens its change of sign around the tangent point when the graph remains each concave up or concave down. However, the sign of f of x minus gx does change its sign when the graph of f of x changes its shape from, let's say, from concave up to concave down, like this one, or conversely concave down to concave up here. This point, I guess everybody already know that this point is, we say, inflection point, this point we can figure out that the sign of the second derivative of f of x changes its sign. Inflection point, let's say x equals b, its sign around x equals b. When the sign of second derivative changes its sign, changes around a certain point x equals b, then the shape of graph of f of x changes from concave up to concave down, or concave down to concave up, and we call it an inflection point. So this problem, all the thing is related to inflection point of f of x original function here. So next step, let's figure out the inflection point of the f of x. Let me erase. Since f of x is periodic function, it could have many inflection points here. Let's focus on the graph here. So inflection point appear here. Here, inflection point appears here, and then here, pi over 4, 3 times pi over 4, and then here, pi. This is important because you can see this point here, concave up and concave down. So pi is an inflection point. If you let me finish this one first, and then another inflection point. I see you get the point here is 5 times pi over 4, and another inflection point is here 7 pi over 4, and another one will be 2 times of pi here. You see this one is concave down and concave up here, so 2 times pi and so on. The next one probably will be 2 pi plus pi over 4 and 2 pi plus 3 times pi over 4 and so on, 3 pi, this one, okay? So if we make a sequence here, pi over 4 will be the first term, and 3 times of 4 will be second term, and so on. So fourth term, fifth term, and sixth term. So you can find the value of a sub 6 minus a sub 2 will be 2 pi minus 3 times pi over 4, and you can figure out the value after you multiply 100 over pi by 2 minus 3 times pi over 4 each quantity. The last comment that I want to make here, when we find the inflection point of x, we could consider the second derivative of fx. So if you remember, the first derivative is 1/2 times sine of 2x when it's between 0 to pi, and negative 1/2 times sine of 2 pi when it is between pi to 2 times pi, and take another derivative here, and then we have f double prime. Derivative of sine gives us a cosine of 2x, and by the chain rule we have another factor 2 here. In this domain we have negative 2 times sine of cosine 2x over 2 here, and then this constant factor disappears here, minus here, minus cosine of 2x, cosine of 2x here. We have to check the point where second derivative of f is 0. So in this case, if we put this one as 0, then we get x equals pi over 4 and 3 pi over 4 here. Okay, and then another one, in this reason we take an equation, negative cosine of 2x equals to 0 gives us zeros solutions of x equals 5 times pi over 4 and 7 times pi over 4. But you should be cautious that we have another like inflection point like pi or 2 pi. Where does this come from? It comes from not this equation, but f double prime changes its sign. So nevertheless, inflection point is non-zero. Its second derivative value is non-zero at the inflection point, but it can change its sign. For instance, when x equals pi, its double second derivative in this case is 1 here. When x equals pi, let me take a limit. X goes to pi minus the second derivative of x. Its value here, you see the minus sign, it's a negative 1. So even though the second derivative is non-zero, but it changes its sign, the sign of second derivative at the around the point of x equals pi. So it's the same for the integer times of pi, 2 times of pi, 3 times of pi, 4 times of pi, and so on. This is an extra inflection point. Let's just say extra inflection point. So let's summarize this problem. This problem could give the student, task takers, extra difficulty because first, it's rather not straightforward to resume the graph of its original graph f of x from the its derivative. That's the first one. And then second, it's not easy to figure out the meaning of the function of h of x. We know the derivative of h of x is just we plug in this variable x to this integrate f of t minus f g of t here. But the meaning of this one, since the function g of x is a tangent line which is related to its original function f of x, it changes the sign of h prime of x. It involves to the inflection point of f of x. This is crucial part to approach this core of this problem. So if you get the this part, I need to figure out the inflection point, and there's another trap. Let's just say trap here. You have to exactly understand the meaning of inflection point. Inflection point, it does not mean the second derivative is 0, but the second sign of the second derivative changes its sign around point, let's say x equals b, certain point, and then it is called the inflection point. And then the magnitude of original function and its tangent line, it crosses through the this inflection point. So okay, this is the whole point. Thank you.